on this computer. Here we go. So welcome. Thank you for being here. Could you please introduce yourself and tell my students what your job title, what your role is?
So my name is Raymond Mackey. I am the Associate Director of Mechanical Services here at Longwood Gardens. That's a fancy title for basically a maintenance supervisor. I have a group of guys that take care of the fountains, all the water features, some of the non-glamorous things like the toilets and the wastewater plant, irrigation and some other things. So if it's got water in it, we usually deal with it. I also am in charge of the boiler operators, which we have some large steam boilers which generate steam throughout the plant for the winter. And without steam, we wouldn't be able to keep our plants alive through the winter, so they're very important. So with that, I went to school at Penn State for mechanical engineering. I've had a number of different jobs, which gave me a pretty diverse background. But I love equipment, love working on, love solving problems. So we'll go from there. How's that?
Wonderful. Thank you. That's great. Good to know what even got you there with this. Now, when did you start at Longwood?
It's been almost 4 years ago now. Yeah.
Gotcha.
Actually, just over 4 years.
Excellent. In your time there, especially, so 4 years is going to be right around when they had the big renovation and renewal and things were way more tech. And we did get the opportunity, as you know, to see some of the science teachers, to see underneath your vast network of tunnels and all the piping. Really impressive stuff under there. But my next question, is there a specific feature in the fountains or in a display that most people think is super impressive, but you, especially from the day-to-day workings, you say, that one's actually pretty simple, not that much to it. Anything like that?
So the big gem of our garden is the main fountain garden, which you alluded to, which we have renovated. It was just about 4 years ago when we brought it online. I came right at the end of the renovation and was lucky enough to learn that system and got very intimate with it to understand how it worked and all the different personalities, let's call it, of the equipment. And by the time I think you came along for the tour, we have worked out a lot of the bugs and learned a lot about operating the system. There are many other fountains and displays, but the main fountain garden is probably the most impressive. There are, I forget how many nozzles, but on the certain basket weaves, there's 1,200 nozzles alone. They're very small, but there are that many nozzles. The main jet in the middle of the rectangular basin, or as we call it, the rec basin, shoots about 175 feet in the air, and that's pretty impressive. I've had a lot of people say, oh my gosh, that must be a huge amount of pressure. And really it's not. It's a large pump, it's a large motor, it's a 100-horse motor, and it's a large volume of water. But through the technology of nozzles, which you may have discussed with your students, you can increase the velocity and get a high squirting fountain, and looks pretty spectacular. We have some robotic nozzles. They're a little more complicated because they tend to take a little more maintenance. Lots of moving parts, electronics, the signals, the communication. So that's an interesting aspect, which my guys, typically being plumbers, aren't used to finesse and working with very fine motion and movements like that. So that would probably be the most, I guess, impressive thing. We have other fountains that are very common and very simple. They use no more than like a sump pump buried in a pit somewhere to give small squirt of water out of a flower or something of the sort. So we have a wide range of pumps and displays.
Yeah, you said 1,200 nozzles on the basket weave design?
Exactly.
That's incredible.
There are 40 nozzles in about a 30-inch ring, and there's 30 what we call octagons. So there alone is 1,200.
Wow.
Yeah.
When you were mentioning the robotic nozzles, I can picture those in the fountain, the rec basin there, how they will move around and have this
Exactly.
place. And I just had a separate thought with that. I don't know if we talk also about space stuff and about rocket launches. And I don't know if you've seen any of the recent, even some of the SpaceX stuff, the nozzles that are actually controlling the engines
Yeah.
and how they articulate and move around beneath something like one of the rocket ships of that.
Sure.
Remind me a whole lot of the motion of what I've seen for the top
Yeah.
of your nozzles. Even though yours are sometimes done by plumbers, it's basically rocket science for what you guys are handling down there. Pretty similar design, I would think.
I would say it's very similar. We use if you can hold on a second, I got a little visual
Sure.
here. This is what we call a ball nozzle. So this ball end is encapsulated in a housing, and the top part is either it has a nozzle on it or it's mounted somewhere, but this can rotate, ball and socket type of mechanical joint, and that's what allows us to get the rotation and movement. Then electric motors actually operate it through linkages and whatnot. So yeah, it's a neat little thing, and it's very similar probably to the way they do the rocket direction
Very cool.
thrusters.
Excellent. Thank you. We'll move on to my next question here. So I know that Longwood's fountain display is full of mind-boggling statistics regarding flow rate, fountain height, number of nozzles, overall quantity of water in a given tank. What would you call, I know you just told us about the 1,200 nozzles, about the 175-foot jets there, but what are some of the other impressive stats that you might be able to throw out there for our students, my students?
So we have, in the main fountain garden, we have 4 different reservoirs or sumps, as we call them. And the smallest one is about 58,000 gallons. The next larger goes to about 91,000 gallons. And then the rec basin is about 158,000 gallons. But the biggest one that we have is the outdoor display, the eye of water and the pear-shaped basin, which is an outdoor display. You go up on the hill behind the main fountain garden, and it is an oculus where the water comes up out of the middle, overflows, runs down an outdoor stream, man-made waterfall, and into a pool, and that's 350,000 gallons. So that's a separate sump. Because of being outdoors, there's a filter called a leaf catcher. It's a really industrial-sized filter. It's a conveyorized belt that is perforated, so water can flow through it, but it's fine enough that the debris, sticks, leaves, and whatnot doesn't go through it. We find all sorts of things. We get frogs and snakes and dead animals and different things like that that fall into the water and end up in our filter. So it's a little interesting that we, whatever we may find in the morning when we come in for that.
I wasn't doing the math in my head quite fast enough as you're going through. It sounded like we were approaching 1 million gallons total.
I would say pretty close, yeah.
Okay.
Yeah.
Maybe I'll go back in the recording or have my students add it up there. But it sounded like between the 350, the 68, the 100 and some, it's definitely over 500,000 and approaching 1 million gallons.
Yeah. Yeah, and it's obviously the largest fountain we have. There's the outdoor air theater, open air theater is very small and very crude in comparison. The sumps are just cinder block walls, and you could barely fit in them compared to the ones that we have at the main fountain garden, where you could drive a truck through if you could get it in there. They're huge. So the Italian water garden is another, it's a very classic European style garden. Lots of small nozzles. It is automated, it changes. A lot of people neglect some of the other fountains because we had so much notoriety with the main fountain garden. But the pump house is much smaller, a little tighter, and again, the sump isn't quite as big, but still very impressive as far as what it does. People just love to see water squirting in the air.
Absolutely. Okay, we'll get on to the hard question here. And whatever of this is most relevant for you, I don't know your day to day, but you mentioned that I know at least part of this. So my students really did some projects where they were explaining Rayleigh-Taylor instability, which has to do more with how different densities and temperature fluids mix, laminar and turbulent flow, which I would think laminar flow especially, and avoiding turbulent flow might be something that you have to deal with. Bernoulli's principle, cavitation you mentioned. Kelvin-Helmholtz is more about fluids flowing on top of one another when they're slightly different densities or temperatures. So I just name dropped a bunch of them. Some of these have to be, I would think, things that are just pretty rare. You don't run into them that frequently. Other ones are probably part of your day-to-day things you have to be worrying about. So which of these are ones that you're like, of course, all the time, this is something I have to deal with versus never have to touch on?
Cavitation is our biggest problem. It doesn't seem to matter where we are, we have problems with cavitation, and cavitation could be very devastating to some of the pumps. I don't know how I could do it. I had a picture of a brand new impeller out of a pump compared to an old one that was badly damaged, and it was half the size basically. It was amazing that the pump actually worked, and it actually started not to work at that point. But we had a lot of issues at first at the main fountain garden with cavitation. And I kind of had to go back and dust off my engineering books to kind of figure out some of the issues. And unfortunately, some of the designs didn't take into account this problem, which, you know, when you show a pipe connected to another pipe at 90 degrees, nobody would think to insert that pipe into the larger header pipe to reduce cavitation, for example. You have a sharp edge, which, you know, that can cause a lower pressure, which is going to increase your cavitation. I assume that you went through cavitation, what it is and how it works and what it does. It's an interesting thing. It sounds like you got a box of rocks in your pump, and you know pretty much right away what's going on when that happens. But we ended up changing some drive parameters on our pumps to operate at different speeds. We didn't have a lot of choice in the design, the way the things were already made, and the piping arrangements and whatnot. So we did what we could, and we still have occasions where we can see it, hear it, and you see the effects of it.
Some of my students, when they were doing presentations on cavitation, they would use some submarine propellers and talk about, I think the famous one they're using was the Pennsylvania submarine, that basically increased the number of blades and slowed down the rate, and that helped them achieve a similar flow with less cavitation. But yeah, it's fascinating. You wouldn't expect it to be as devastating as it is.
Yeah.
It's interesting technology there. So that's a problem-solving one that you as in maintenance you have to deal with and be ready to handle. But other ones, like I would think laminar flow kind of just happens. Like you end up with that pretty bubble. One of your fountains, basically it comes out of the nozzle and you've got that nice uniform. Do you have a name for that one? I don't know if you know what I'm thinking about. The one that looks bubble there?
We're working on that right now, and I can't remember what they call that. I know what you're talking about.
That's beautiful laminar flow, the nice uniform.
There are. And they have different nozzles that, of course, as soon as you increase the velocity, you start to get into turbulent flow pretty quickly. So there are people like Fluidity and others have designed nozzles to create a laminar flow and make a very clear stream, and it's actually pretty cool. The most of our flow would be turbulent. We do, you know, with say Bernoulli's equation, more on the AV1, AV2, you know, we try to slow down the momentum of the waters to stop the pipe hammer effect. When they built the main fountain garden, they used PVC or plastic pipe. Now it's pretty thick and heavy pipe, but it still doesn't take the shocks of water moving quickly and going around corners. And then with our shows, we open and close valves quickly, and that stops water fast and gets it moving again quickly. So we had some failures on our PVC pipes, and some of them were 12-inch diameter. So you're talking a pipe that's, you know, pretty decent size with a wall thickness of close to an inch thick.
Wow.
And it didn't hold up very well, I can tell you that. So we've changed out some of that pipe to stainless steel. And, you know, guys were asking me, you know, why is this pipe so big? But then once you get up to the nozzle, you're down to, you know, a 2-inch nozzle. So you got a 12-inch line going to 2 inches. So if you did that math, the volume of the amount or mass flow rate doesn't change. The area changes and gets smaller, so therefore the velocity increases, and that's how you get a nozzle that shoots 175 feet in the air.
So that's interesting. It's that, and I've been underground there. So you have the real thick, the 12-inch diameter, so that you can maintain a pretty slow flow rate, but then still by the time it narrows down to the thin nozzle, get fast velocity with a similar amount of, do you measure gallons per second, or what's your normal unit that you guys use?
Typically, I think those pumps run about 2,500 gallons per minute.
Gallons per minute. Gotcha.
Yeah.
Wow.
So a safe flow rate inside of a pipe is typically 10 feet per second. So if you start to increase over that, you risk, you know, blowing out an elbow, so to speak.
Yeah.
If you go around a corner somewhere. So you keep it somewhere below 10 feet per second in velocity. So the way to do that, increase the pipe size, the water flows slower, and then when you get to where you're going, decrease that pipe size and you can increase velocity.
Very cool. I love it. Thank you. That's great. My final question for you. Do you have any fun stories related to fluid dynamics where you or your coworkers, your knowledge of physics, your knowledge of science helped you solve a problem in an unexpected way?
That's a tough one. I don't know if I got down that far to your question.
It's okay.
Well, you know, I would say that some of these replacements of pipe, we saw a lot of when a show is going on in the main fountain garden, and if you're in the pump room, you'll see the pipes move a lot. So we've since installed expansion joints to give it some flexibility. We've braced things, added bracing to keep it from moving. Of course, changed materials. So we've done a few things in that respect. Physics-wise, you know, I should probably look harder at my physics background and try to get some use out of it. But I can't think of a very specific example for you. I'm sorry.
Well, no, even what you already told me was already getting to this. When you're talking about Bernoulli's and the flow rate and that, like that is preventing them from blowing out and keeping your reducing replacements and keeping it within the 10 feet per second. Like you were given a bunch there. You were already definitely answering this one. I'll give on a bonus follow-up that I just thought of, because I think this happened since I might have first emailed you. You guys announced the big renovation of the conservatory and that huge new project there. I don't know the intricacies, the ins and out of that very well, as far as I'm imagining Longwood, the historic, every part of it there's going to be water displays and there's going to be things. So are you at all involved in that process, or is it more they're going to set it up and you're going to have to pick up the pieces and figure out how to make it stay operational?
Now I have a pretty good stack of prints downstairs right now that I am supposed to be reviewing to make sure that the piping meets our specifications and that it's rounded the way we want it, and there's valves in the proper places and all that type of thing. The pump sizing and the types of pumps, we have specifications for a lot of that stuff so that we get a similar pump to what we've had in the past. We don't have to keep a lot of parts on the shelf. We know who to go to get things fixed, and you know, we can call people up if we need help. So there's a lot that luckily they do involve us in. Certainly adds a little to the workload, but it's a good thing because once we're handed over this new project, we know how it works or how it's supposed to work, and we hopefully got what we asked for.
Wonderful.
Yep.
And sorry, I thought of one additional tiny piece. When I was there with you, when we were underneath the facilities, I don't remember if it was you or somebody else was showing us how the fire on the water worked. And we were amazed at the simplicity of that. Like it wasn't, yeah, it's an amazing, impressive nozzle. It's a trade secret as far as the exact bits of it. Not many people are using it. But am I correct that it's basically, was it propane?
It is propane.
Basically propane injected into the water and lit?
Sure. So there are, the nozzle is a German-made nozzle, and it's probably about 4 feet long, but it's got a venturi in the middle, which I'm sure you know what a venturi is, and I hope your students do too, but it's a neck down area, which again would increase velocity at that point. So in that area, they had 2 cartridges, which look like, this looks like a screen or a mesh material. And below that area, the main gas is injected so that it has to travel through all that screen and mesh. And it acts like the little aerator that's on the end of your faucet in your kitchen. It makes the water frothy and aerated. So this device circulates and mixes that gas into the water stream. So when we turn the gas on, you can immediately see it change from what looks like a very laminar, clear stream of water about 1 inch in diameter or so to a very frothy looking stream. The other part of that is a pilot gas line. So much like your gas grill, there's a couple small lines of pilot gas that is actuated by a little arc. And of course it's being splashed with water, so we have to do that many times, and I don't know, there's 50,000 volts there to give you this arc, which it gives it a ignition, and it starts igniting the propane, which is heavier than air, so it ignites it at the base of the nozzle, and as that gas is carried up the stream, the flame will carry up to the top. And
Amazing.
it is pretty amazing, very simplistic, but it works. And we mix water with fire.
That's very cool. And I'll admit, I don't know that word. Venturi? How do I spell that?
Really? I'm surprised.
Well, yeah,
It's
I need to look this one up.
Venturi, I believe, Venturi.
I will have to look that one up to make sure I teach my students about that one because I don't know that one off the top of my head. So thank you.
Well, you look like a younger man. If you had a carbureted car, carburetors work on a Venturi principle.
Huh.
They suck air down through a neck down area. If you use a straw, you stick a straw in a cup and you blow air across it, it'll actually wick the liquid up the straw and it'll blow out in a stream.
I do that. I have the straws right over there. We do that but I teach that as Bernoulli's because you make the fast moving air, so then you get the low pressure from Bernoulli's principle and it gets drawn up toward the low pressure. But I will have to look into, make sure I include the Venturi in the future. So
there you go.
For that. I appreciate it. Well, I appreciate your time. Thank you for being willing to talk to my students about this. I look forward to being able to share this with them. Enjoy your vacation.
Thank you.
I look forward to enjoying your gardens and sending my students there in the near future.
Well, I hope to see you again in the gardens, and if there's ever a time I could visit your class, I'd love to. So.
Wonderful. Post-pandemic, we'll have to invite you over.
Absolutely.
Thank you. I'm going to hit stop recording right here.
All right.